When a standard rifle is fired, the loudest sound isn't always the explosion at the muzzle. If the bullet travels faster than the speed of sound, it pushes a rippling shockwave through the air. That microscopic sonic boom announces to anyone listening that a shot has been fired, and it draws a straight acoustic line back to the shooter. This animation illustrates the problem with traditional silencers. A standard suppressor catches the expanding gases at the end of the barrel, muffling the muzzle blast, but it does absolutely nothing to stop the supersonic crack of the bullet itself in mid-flight. To eliminate that mid-air crack, there is only one physical solution. The bullet cannot break the sound barrier. It must be intentionally slowed down to a subsonic velocity, staying below roughly 343 meters per second. For covert operators, the weapon's firing mechanism is a secondary issue. The actual threat is the physics of supersonic flight. As long as a bullet flies faster than sound, standard stealth attachments are physically incapable of hiding the shooter. During the Cold War tensions of the 1970s and 1980s, Soviet intelligence and special operations units, the KGB and Spetsnaz, faced a strict tactical requirement. They needed a weapon system for clandestine operations that could strike a target without generating any acoustic signature. The initial attempt was to modify standard-issue infantry hardware. The Soviets took their widely used AKM rifles and bolted on PBS-1 suppressors, loading them with subsonic variants of their standard 7.62mm ammunition. This created a severe tactical problem. A standard bullet stripped of its speed is also stripped of its kinetic energy. By keeping the 7.62mm round subsonic to maintain silence, it lost the power necessary to penetrate a modern NATO flak jacket at an engagement distance of 400 meters. Soviet designers were forced to find a workaround for a basic mechanical trade-off. To succeed, they had to create a projectile that maintained lethal kinetic energy while restricted to the low velocities required for silence. At the SNI Tochmash Research Institute, engineers moved the focus away from the rifle itself. They began with the requirement for armor penetration at subsonic speeds, a goal that could only be met by designing the ammunition first. They took a standard 7.62 by 39mm AK-47 casing and widened the neck. This allowed it to house a massive 9.27mm projectile, creating an entirely new cartridge, the 9 by 39mm. Instead of relying on a fast, lightweight dart, the new cartridge substituted mass for velocity. Acting as a heavy, slow-moving hammer, it generates severe impact force subsonically. The SP5 variation prioritized accuracy, while the SP6 featured a hardened steel core for armor penetration. That steel core allowed the SP6 to punch cleanly through 8mm of solid steel at a distance of 100 meters, all while moving slower than the speed of sound. This heavy subsonic cartridge provided a mechanical solution to the problem of lethality. By optimizing the bullet's mass, the Soviets ensured the round could punch through armor without ever triggering a supersonic crack. With the ammunition perfected, they built a host explicitly to fire it. This is the VSS Vintorez, designated the 6P29 and nicknamed the Thread Cutter. Looking at a cross-section, we see gas bleed holes drilled directly into the barrel. As the bullet travels down the bore, expanding gases vent outward into a surrounding expansion chamber. The gas hits a precise baffle stack, dissipating pressure and minimizing exit noise. This compact breakdown system was issued directly to Russian special forces, seeing extensive use in covert applications across urban combat zones, from the Chechen Wars to the modern conflict in Ukraine. The Vintorez functioned because the rifle and its ammunition were developed as a single integrated system, engineered specifically to operate within the narrow physical window below the sound barrier. This graph illustrates the severe ballistic penalty of subsonic flight. While a standard supersonic sniper round maintains a flat, extended flight path, the heavy 9 by 39mm cartridge follows a steep, plunging arc. Moving so slowly, gravity pulls the bullet down faster relative to the distance it travels, restricting its effective range to roughly 400 meters. That aggressive bullet drop meant the Vintorez could never function as a general-purpose infantry rifle. It remained a rare, highly specialized tool, reserved exclusively for close-range clandestine missions. Yet, despite its rarity in combat, the rifle achieved massive fame in global pop culture, driven by its frequent inclusion in popular modern video games. On screen, players experience a digital myth. The weapon is often portrayed as a flat-shooting, long-range sniper rifle that ignores gravity, erasing the very physical compromises that defined its creation. The true legacy of the Vintorez is one of strict physical constraints. It is an instrument that achieves absolute stealth, not through mechanical magic, but by accepting the harsh compromises required by the laws of physics. The Soviet Union committed to this specialized engineering path in 1987, but even as the Vintorez proved its effectiveness for clandestine units, it raises a question. Why did it take Western militaries over 2 decades to field their own dedicated subsonic platforms?